Hello everyone, I'm Ruchita Gandhi. Today my team and I are going to present the topic cache coherence. It's a topic that might seem complex at first, but I assure you by the end of this presentation, you'll have a solid grasp of its importance and implications. Before we get into the technical details, let me outline what we will cover today. These are the contents we will be covering today. Introduction to cache coherence principle, cache coherence protocols, advanced protocols MESI and MOESI, implementation in Intel i7, implementation in AMD, performance implication of cache coherence strategies, comparing protocol performance, case studies on coherence protocols, technological impacts on cache coherence, conclusion, and the navigating the future of cache coherence. Now picture this. A world where computers are interconnected with multiple processors sharing access to memory. It's an exciting concept, but it also brings its fair share of challenges, particularly in ensuring data consistency across this interconnected processor. That's where cache coherence comes into play. It's essentially the mechanism that ensures all processors in multi-core system have consistent view of shared data. It's like ensuring everyone sees the same version of document, regardless of where they are accessing from. Throughout this presentation, we will discuss about the complexity of cache coherence, understanding why it's crucial for the seamless operation of modern multi-core processor. Let's start with the introduction. Today, we are exploring cache coherence and the vital concept in the computer system. Simply put, cache coherence ensures that when multiple processor shares access to memory, they'll all see the same version of data. This is crucial for maintaining data consistency and preventing errors in system with multiple cores. Think of cache coherence as referee in a game, ensuring fair play among all players. In a computer system, it's like the traffic controller, ensuring smooth flow on a busy road intersection. So let's dive into it and uncover all the cache coherence keeps our system running smoothly. Now, let's discuss about the cache coherence principles and the cache coherence versus consistency. First, let's differentiate between the coherency and consistency. Coherency ensures that reads and writes to the same memory location behave predictable across multiple processors. On the other hand, consistency governs how access to different memory locations are handled. Now, let's focus on the three key properties of coherence. The first one, read after write consistency. Ensure that a read operation following a write operation by the same processor and returns the written value. And the second one, separation of reads and write. Guarantees that a read operation following a write operation by another processor and returns the written value, provided there are no intervening writes. And third one is serialized writes order. Ensures that write to the same location by any two processor are observed in the same order by all the processor. These principles forms the foundation of cache coherence, ensuring that data remains consistent and reliable across multiple processors. Coherence within a memory system ensure that any read operation returns the most recently written value of a data item, maintaining consistency across multiple processors. This means that regardless of which processor performs a read operation, it should always receive the most up-to-date data. Understanding these three principles is crucial for addressing the challenges faced in maintaining coherency and consistency in multi-core system. This sets the stage for exploring cache coherence protocols and the solution in subsequent slides. In this slide, I will be discussing about the cache coherence problem arises because multiple processor in multi-core system may have different views of memory due to their individual caches. These can lead to inconsistency in the values of shared memory location. It is illustrated in the figure 5.3 as shown here. Now let's discuss about this problem. In the above figure, a scenario involving two processors, which is A and B, accessing the same memory location X. Initially, neither processor cache contains X and its values is 1 in memory. Processor A reads X, updating its cache and memory to 1. However, before processor B accesses X, it still holds the old value of 1 in its cache. When processor B reads the X value, it retrieves the outdated value from its cache instead of the updated value in memory. This discrepancy in the data seen by different processor highlights the cache coherence problem. It demonstrates how inconsistent views of shared data among processors can lead to errors and inconsistency in computation. In this slide, I will be discussing about the enforcing coherence. Coherent caches plays a crucial role in this process. They serve as a backbone for facilitating the migration and replication of shared data items across multiple processors. By doing so, they effectively reduce latency and contention, ensuring that data access remains efficient and consistent. When it comes to implementing cache coherence protocol, there are two main approaches. The first one is hardware and the second one is software solution. Hardware-based protocols, which are focusing of our discussion, are preferred for their efficiency and effectiveness in managing coherence. These protocols are integrated directly into the hardware architecture of multi-core processor, allowing for seamless enforcement of coherence rules and minimizing the overhead associated with software-based solutions. By leveraging hardware-based cache coherence protocols, modern computing systems can efficiently manage shared data access, ensuring optimal performance and reliability across all processing cores. Let's talk about the cache coherence protocol, which are like the organizer behind the scenes. These protocols basically keep track of who's sharing what data across all the caches in our system. They're kind of like the coordinators at a big event, making sure everyone gets their fair share of the action. Now, there are two main types of cache coherent protocols we need to know about. One is snooping protocols and another is directed based protocols. Let's talk about the snooping protocols. These are like the detectives of our system, always snooping around to see who's got what data. They are used in system where information needs to be broadcasted to all the caches so everyone stays in the loop. Then we have the directed based protocols. These are more like the organizers of a big meeting, keeping track of who's got what data in centralized or distributed way. They are like the central hub for making sure everything stays organized and efficient. Understanding these different type of cache coherence protocol helps us see how data sharing works in multi-core system. It's all about finding the right balance between efficiency and organization, and these protocols are key to making it happen. In this slide, I'll be discussing addressing the cache coherence problem. So in multi-core system, here is the issue. Each core cache might have old, outdated data, which can mess up how we share memory between them. It's like having different version of same book floating around, and nobody knows which one is the latest. Now, how do we fix this? Well, we got a couple of solutions for the above problem. First of all, we got cache coherence protocols. These are like the rule books that make sure all the cores see the same version of shared data. They are the referees on the field, making sure everyone plays by the same rules. Then we got the implementation strategies. These are like the game plans we used to put those protocols into action. We got directory based strategies and snooping strategies, each with their own way of keeping track of data, making sure everything stays in sync. Now, why it's so important to address this coherence problem? Well, think about it like this. Without coherence, it's like trying to build a house with mismatched bricks. It won't work right. So coherence ensures that everything behaves consistency and reliable in our shared memory systems, which is absolutely crucial for making sure our parallel application runs smoothly and correctly. So by understanding and addressing the cache coherent problem, we are laying the groundwork for a strong, reliable computing system that can handle anything we throw at it. Now my teammate Shravani will discuss more about the cache coherence protocol.
Now, let's look into the cache coherence protocols in detail. Cache coherence protocols serve as the backbone of multiprocessor systems, ensuring the integrity and consistency of shared data across various caches. In these systems, multiprocessors may concurrently access and modify the same data, leading to potential inconsistencies if not properly managed. Cache coherence protocols address this challenge by coordinating data access and ensuring that all processors have access to the most up-to-date information. Without these protocols, the system would be prone to data corruption, which will be resulting in the incorrect computations and unreliable performance. Therefore, understanding the principles and mechanisms of cache coherence protocols is essential for designing efficient and reliable multiprocessor systems. So we have two primary approaches. One is snooping and directory based protocols. Snooping protocols characterized by their continuous monitoring of the shared bus excel in smaller scale systems due to their simplicity and efficiency. Meanwhile, the directory-based protocols offer centralized management of cache coherence through a directory that tracks the status of data blocks. Each approach has its advantages and implementation challenges, making it crucial for system designers to carefully evaluate their requirements and select the most suitable protocol for the specific application and scalability needs. So, the snooping protocols operate by continuously monitoring the shared bus connecting all processes in the system, which we have already told in the before slide. So whenever a processor performs a read or write operation, all other processors snoop on the bus to detect and manage any changes to the shared data. One common method employed by snooping protocols is the write invalidate protocol, which ensures exclusive access to a data item before writing by invalidating other copies in different caches. This protocol enforces with serialization, preventing multiple processors from simultaneously modifying the same data. Additionally, snooping protocols utilize finite state machines to manage cache block states effectively, ensuring coherence and managing cache block ownership efficiently. These mechanisms are crucial for maintaining data consistency and preventing data corruption in multi-processor systems. So now let's look into an example to understand it better. So let's take two processes named A and B. So this is a scenario where processor A reads data item from X and also the processor B reads the same X. Processor A then writes a value 1 to the X. So then processor B reads X again as that need to be updated. Snooping protocol ensures coherence by invalidating any other copies of X when processor A writes to it, ensuring the processor B fetches the updated value from memory or the cache of processor A. So, ensuring that all processors have access to most up-to-date data. State transitions in snooping. Snooping protocols rely on state transitions to manage cache block states effectively. These states typically include invalid, shared, and modified, representing the different states of a cache block across multiple processors. State transitions occur in response to processor requests and bus activities, ensuring coherence and managing cache block ownership efficiently. By modeling cache coherence protocols as finite state machines, designers can analyze their behavior, identify potential problems, and optimize their performance. So, this diagram shows a finite state transition diagram for a single private cache block using a write invalidation protocol and a write back caching. For simplicity, the three states of the protocol are duplicated to represent transitions based on processor requests as opposed to transitions based on bus requests. Boldface type is used to distinguish the bus actions as opposed to the conditions on which a state transition depends. The state in each node represents the state of the selected private cache block specified by the processor or bus request. All of the states in this cache protocol would be needed in a uniprocessor cache where they would correspond to invalid, valid, or dirty states. Most of these state changes indicated by arcs in the left half would be needed in a write back uniprocessor cache, with the exception being that invalidate on a write hit to a shared block. The state changes represented by the arcs in the right half are needed only for coherence and would not appear at all in the uniprocessor cache control. There is only one finite state machine per cache, with stimuli coming either from the attached processor or from the bus. So this diagram shows how the state transitions in the right half of these diagram are combined with the left half of the same diagram to form a single state diagram, which I have shown before, that is this one, for each cache block. To understand why this protocol works, observe that any valid cache block is either in the shared state in one or more private cache or in the exclusive state in exactly one cache. Any transition to the exclusive state, that is, which is required for a processor to write to the block, requires an invalidate or write miss to be placed on the bus, causing all local caches to make the block invalid. In addition, if some other local cache had the block in exclusive state, the local cache generates a write back, which supplies the block containing the desired address. Finally, if a read miss occurs on the bus to a block in the exclusive state, the local cache with the exclusive copy changes its state to shared. So, in this, the actions in gray, which handle read or write misses on the bus, are especially the snooping component of the protocol. One other property that is preserved in this protocol and in most other protocols is that any memory block in this shared state is always up to date in the outer shared cache, which simplifies the implementation. The black activities represent state transitions induced by the local processor, while the gray activities represent transitions induced by the bus activities. In fact, it doesn't matter whether the level out from the private cache is a shared cache or memory. The key is that all accesses from the cores go through level. Although our simple cache protocol is correct, it omits a number from complications that make the implementation much trickier. The most of these is that the protocol assumes that operations are atomic. That is, one operation can be done in such a way that no intervening operation can occur. Non non-atomic actions introduce the possibility that the protocol can deadlock, meaning that it reaches a state where it cannot continue. We will explore these later. The basic mechanisms. The key to implementing an invalidate protocol in a multi-core system lies in utilizing the bus or another broadcast medium to perform invalidates. When a processor writes to a shared block, it must acquire bus access to broadcast its invalidation, ensuring coherence across all caches. This processor serializes write operations, preventing conflicts between processors attempting to write to the same data simultaneously. Additionally, snooping cache protocols must track cache block states and transitions effectively, ensuring that all processors have access to the most up-to-date data while minimizing interference with processor cache accesses. Unlike the write and validate protocol, the write update protocol updates all the cached copies of a data item whenever it is written. While the approach reduces the risk of the data inconsistency, it consumes more bandwidth as it requires broadcasting the write to all caches in the system. So, so this is the advanced mechanism, that is exclusive state. So some snooping protocols introduce an exclusive state for cache blocks, indicating that a block is exclusive to a single processor. And the states allow for a more efficient handling of write operations and reduces the risk of data conflicts between processors. The protocol ensures that any valid cache block is either in shared state in one or more private cache or in the exclusive state in exactly one state, facilitating efficient data access and synchronization among processors. So the main challenges and considerations for this is uh, especially in a large scale, so that is bandwidth consumption. Multiprocessor snooping protocols in particular can consume significant bandwidth, impacting system performance. Efficient bandwidth management techniques and optimization strategies are essential for mitigating the impact of snooping on system performance. So, additionally, real world implications of cache coherence protocols must address scalability, complexity, and overhead associated with coordinating data access and ensuring coherence across multiple caches and processors. So, ongoing research and development efforts are focused advanced coherence protocols to meet these demands, emerging applications and architectures, optimizing performance, scalability, and energy efficiency.
Hi all, this is Lahari. So now I will be going through extensions of basic coherence protocol. We have already discussed previously about the basic coherence protocol, which is the simple MSI protocol, modified shared invalid protocol. So there are many extensions of this basic protocol. These extensions are created by adding additional states and transactions that optimize certain behaviors, possibly resulting in improved performance. Two common extensions are MESI and MOESI. MESI adds the exclusive state to MSI, modified, exclusive, shared, and invalid. MOESI adds the owned state to MESI, modified, owned, exclusive, shared, invalid. Let's look at MESI protocol. So it stands for, as we have already mentioned, modified, exclusive, shared, and invalid. It is a cache coherence protocol fundamental in multiprocess systems. It ensures data consistency among caches by categorizing cache blocks into distinct states. Now let's break down these states. So modified is when a cache block is marked as modified, it means that it has been altered and is exclusive to the cache holding it. In other words, this cache holds the only copy of the data and it differs from the corresponding block in main memory. E stands for exclusive. In the exclusive state, a cache block is present in only one cache and it is clean, meaning it matches the corresponding block in main memory. This state allows for efficient read operations without the need for further coordination with other caches. S stands for shared. When a cache block is marked as shared, it means that multiple caches hold copies of the block and these copies are identical. This state facilitates data sharing among processes, enabling concurrent access to shared resources. I stands for invalid, and the invalid state indicates that the cache block is either not present in any cache or is stale. Accessing data in this state requires fetching it from main memory or another cache holding a valid copy. Let's visualize the state transitions in this diagram. So, we'll be discussing this diagram in detail in the further sections. But here, this diagram illustrates how cache blocks transition between the modified, exclusive, shared, and invalid states. Understanding these transitions is crucial to grasp how MESI ensures data consistency among caches. The MESI protocol diagram here visualizes how cache block transitions based on CPU requests, read or write, and bus requests from other processors. This ensures data remains consistent across multiple caches, optimizing performance for scenarios where a single cache reads and writes a block. Transitions occur due to CPU actions, read or write, or bus signals, write, miss, or invalidate. Here, this diagram highlights the write back nature of the protocol. No transitions directly from modified. MESI reduces bus traffic and invalidations, leading to improved performance. Let's look at some benefits of MESI. MESI is optimized for scenarios where a cache block is read by a single cache before being written by the same cache. This optimization minimizes unnecessary data transfers and ensures efficient utilization of cache resources. By reducing bus accesses and invalidations, MESI improves system performance. With fewer bus transactions required to maintain cache coherence, system bandwidth is preserved and latency is reduced, leading to overall enhanced efficiency. One real-world application of MESI is the Intel i7 processor family, which employs a variant known as MESIF. This variant introduces additional optimizations such as the forward state to further enhance performance in distributed memory organization. Let's look at MOESI protocol. So it is an extension of MESI cache coherence protocol that plays a critical role in maintaining data consistency in multiprocess systems. MOESI stands for modified, owned, exclusive, shared, and invalid. Introduces additional states to enhance cache coherence. So now let's break down the states. Modified. Similar to MESI, the state indicates that the cache block is modified and exclusive to the current cache. And owned, a unique addition in MOESI, this state signifies that the cache block is owned by the current cache but is out of date in memory. This allows caches to remain its ownership of modified data without immediately writing it back to memory, thus optimizing performance. And E stands for exclusive. Just like in MESI, the state denotes that the cache block is exclusive to one cache and is clean. Shared. The shared state indicates that the cache block is shared among multiple caches, facilitating efficient data sharing and access. Invalid. Similar to MESI, the state signifies that the cache block is invalid or not present in any cache. MOESI protocol improves cache coherence by introducing the own state, which enhances the system performance by reducing unnecessary write backs to memory. This optimization minimizes bus traffic and improves overall system bandwidth and latency. So, this diagram references the state transitions of the MOESI protocol. It shows the cache block state transitions where here we introduce the own state, allowing a processor with the only copy to directly provide data to others, reducing unnecessary writebacks and improving performance. This is used in AMD Opteron processors for better efficiency. The diagram shows the state transitions for write-back caches used in multiprocessor systems. The state transitions are triggered by CPU requests and bus requests, similar to MESI protocol. So, here are some of the benefits of MOESI protocol. Reduced bus traffic. By introducing the own state, MOESI reduces unnecessary writebacks to memory. When a processor has a block in the own state, it knows it is the only copy and doesn't need to immediately write it back on a read miss from another processor. This reduces bus traffic and improves performance. Improve performance. The reduction in bus traffic due to own state leads to overall better performance for the system. MOSI is used in real-world applications such as AMD Opteron processor family. Here let's look at some performance metrics. So the cache hit rate is moderate in MSI protocol, whereas it improves in MESI by allowing more efficient sharing of data between caches. It further improves in MOESI by reducing unnecessary writes to memory. Bus utilization is high in general for MSI protocol, but it reduces the bus traffic by minimizing the invalidations in MESI and further reduces its bus utilization by allowing caches to maintain ownership without immediate writebacks in MOESI protocol. Average access latency. MESI reduces access latency by allowing caches to respond requests more quickly. MOESI further reduces latency by minimizing memory accesses. Optimizations in parallel workloads. Both MESI and MOESI are better suited for parallel workloads compared to MSI due to the enhanced cache coherence mechanisms. Optimizations in multi-program workloads. It's limited in case of MSI. In case of MESI and MOESI, it provides better performance by reducing contention and improving data sharing efficiency. The effectiveness of these protocols in optimizing performance in parallel and multi program workloads will be examined in detail in the next sections. Let's look at some performance optimizing methods with MESI and MOSI. Firstly, these protocols facilitate efficient data sharing between processors by categorizing cache blocks into different states and managing the transitions. MESI and MOSI ensure that processes have consistent views of shared data. This enhances parallel processing performance by reducing data access, latency, and improving overall system throughput. Secondly, MOSI and MESI minimize coherence overhead by reducing bus transactions and cache invalidations. This optimization leads to lower system overhead and improved bandwidth, allowing for more efficient utilization of system resources. Moreover, these protocols enhance system scalability by reducing contention in multiprocessor environments. By efficiently managing cache coherence, MESI and MEOSI minimize conflicts between processors, enabling the system to scale effectively as the number of processing units increases. Furthermore, MESI and MOSI optimize resource utilization by minimizing data transfers and cache evictions. This results in higher cache hit rates and reduced average access latency, enhancing overall system performance. Looking ahead, further research could refine MESI and MOSI protocols to address specific application requirements and emerging computing paradigms. By continuously improving these protocols, we can ensure that multiprocessor systems operate efficiently and effectively in diverse computing environments.
Let's start with the implementation of Intel i7. MSI in Intel i7 processor utilize MSI protocol for cache coherence management. Hardware coherence engine handle scooping and state transitions effectively. Quick path interconnect. High speed point-to-point interconnect replacing the front side bus for the faster data transfers. The QPI connect cores, cache, and integrated memory controllers. Point-to-point interconnect reduces the latency and increases the bandwidth compared to shared bus architectures. Enables direct communications between cores and caches for faster coherence actions. Ring interconnect structure. Cores and cache inheritances are connected in a ring topology for efficient data transfers. Ring allows data flow in both directions, reducing the communication overhead. The performance enhancements. Intel i7 processor employ various optimizations such as victim cache and early misdetection. These techniques aim to minimize coherence overhead and maximize the system performance. So this diagram illustrates a ring interconnect architecture used in Intel processors like Intel i7. The ring interconnect connects various components such as CPU cores, integrated graphics, and system agents, allowing them to directly share and manage cache data. This slide shows the architecture of Intel i7 processor. The processor cores are arranged around the central shared cache. Each core has its own private L1 and L2 caches, and L3 cache is shared between all the three cores. The ring interconnect provides a high bandwidth connection between cores and the L3 shared cache. The interconnect itself showing the bi-directional communication paths, and the size of L1, L2, L3 caches can vary depending on the specific intercore i7 processor model. The MSI protocol operations indicates how the data flow and synchronized across the caches. The diagram shows a sequence where one core modifies the data, marking it as modified, and the subsequent validation messages are sent to other cores to maintain the coherence. Implementation of AMD Optron. AMD Optron has the coherent hypertransport CHT. It leverages the CHT technology for on-chip cache coherence. Also, CHT provides the high bandwidth links between cores, memory, and input-output devices. The hypertransport interconnect has the high-speed point-to-point links for inter-process communication and memory access, which enables the efficient data transfers and scalability in multi-socket systems. Distributed directory structure. The cache coherence information is distributed across multiple directories, nodes for better scalability. Each node manages a portion of the address space and also associated cache line states. Memory mapping. Portion of system memory mapped to the individual processors for the efficient cache access. This mapping schema helps in maintain the data consistency across the distributed caches. Scalability and performance of AMD. The CHT technology and the distributed directories enables efficient cache coherence in large-scale systems. The AMD optimizes coherence protocols and as well as the hardware for the optimal performance in multi-core environments. This is the directory-based system, AMD architecture. So in this diagram, we explore the distributed directory-based cache coherence as used in AMD Optron processors. This is showing us how the coherent hypertransport CHT technology interlinks the multiple process nodes, each with local memory and L1, L2, and L3 shared caches, a directory at each node that keeps track of state of each cache line and which node has the copies of which lines. The hypertransport links between nodes illustrating the communication of the coherence. Typical states and transitions based directory responses to the request from different nodes. These diagrams helps us in understanding the physical layout and logical operations of cache coherence mechanisms and modern multi-core processors, providing an insight into the complexity and efficiency of the design strategies employed by the leading chip manufacturing companies like Intel and AMD. And for our next task, let's do an exercise. So consider an 8 core processor, multi-core, which each processor has its own L1 and L2 caches. Snooping is performed on shared bus among the L2 caches. Assume that average L2 request, whether for a coherence miss or other miss, is 15 cycles. And also assume a clock rate of 3 GHz, CPU of 0.7, and load store frequency of 40%. If our goal is that no more than 50% of L2 bandwidth is consumed by the coherence traffic, what is the maximum coherence miss rate per processor? Pause for a few minutes, try for it your own, or let's go into the solution. First, let's start by understanding the system configuration. We have an 8-core processor where each processor has its own L1 and L2 caches, and snooping is performed on shared bus among L2 caches. Our given parameters are average L2 response time is 15, clock rate is 33 GHz, CPI is 0.7, and load or frequency is 40. So next, let's go with defining the cache cycles available. The formula is clock rate by cycles per request into 2. The clock rate is 3 gigahertz and divided by the cycles per request 15 into 2, which is 30, which gives us the 0.1 into 10 power 9. Similarly, substituting the values in the second equation, where memory references clock or processor into the clock rate times processor count times CMR. Substituting those values, we get 13.7 into 10.9 CMR. So equating the first and second equation, we can get the CMR, which is 0.0073, which is approximately 0.73%. And next, the practical challenges and solutions for the multi-core coherence, cache coherence. Scalability challenges. Increased communication overhead and latency at the number of as the number of cores grows. Maintaining the data consistency across numerous caches requires efficient protocol and hardware. Performance optimization. Optimizing cache coherence protocols and hardware paths minimize the synchronization delays. Techniques like victim cache, early miss detection can improve the overall system performance. Energy consumption management. Cache coherence mechanisms can contribute to increased power consumption. An adaptive power management scheme can reduce the power energy usage while maintaining the coherence. Hardware and software coordination. Efficient cache coherence requires a close coordination between hardware capabilities and software algorithms. Compiler optimization and data placement strategies can significantly impact the coherence performance. Future directions. Research focus on innovative hardware design and coherence protocols and system architectures. The goal is to achieve the optimal scalability, performance, and energy efficiency for the future systems. Next, my team will continue. Thank you.
Hi, my name is Anjali and I'll go over the final part of this presentation, starting with performance implication of cache coherence strategies. So, cache coherence ensures that all processor cores within a multi-core system have the latest data. This synchronization is crucial for preventing inconsistencies that can arise when multiple processors access and modify shared data. Imagine a scenario in an intensive computational task where two cores have different data values for the same memory address. So cache coherence prevents such discrepancies, ensuring all cores work with the most current data. This feature is particularly vital in applications where precision and data reliability are paramount. For example, in financial systems, even a slight data mismatch can lead to a significant error, potentially costing millions. Similarly, in healthcare systems, and accurate data is critical for patient safety and care. Cache coherence directly influences key performance metrics such as system throughput and computational latency. A well-implemented coherence strategy ensures that processes spend less time waiting on data updates, thereby speeding up data access and processing. So, effective cache coherence reduces the time needed to synchronize data across cores, which in turn lowers latency and increases the rate at which processes can be executed, essentially boosting the overall throughput of the system. The efficiency of a cache coherence strategy strongly correlates with the overall system performance. Efficient strategies reduce the overhead associated with keeping the cache coherent, which not only improves speed but also reduces power consumption and heat generation. So, different applications and architectures may benefit from specific coherence protocols. Choosing the right protocol can drastically affect the performance and scalability of an application. For instance, snooping may be ideal for smaller systems with limited core counts, whereas directory-based protocols might be better suited for large distributed systems. So, selecting a cache coherence protocol involves balancing complexity, speed, and resource usage to optimize performance. It's like tuning a car's engine for either a sprint race or a marathon, depending on the need. So, a poorly chosen protocol can throttle system performance akin to using a sports car for off-road conditions. it simply won't perform as well. So therefore, understanding the specific demand of a system's architecture and the typical workload it handles is critical in making an informed decision that ensures optimal performance across all metrics. So, coming to the protocol overview, snooping protocol operates by monitoring or snooping on the communication bus. So, each cache controller watches the bus to check if a data cache it has already cached is being written to by another processor. So, this allows the controller to ensure the cache's data remain current and consistent with changes made elsewhere in the system. So this method is akin to eavesdropping in a conversation to ensure that no one misses out on important updates. So each participant listens in to catch any relevant changes they may need to act on. So snooping typically employs a broadcast method where every write operation by any processor is announced to all processors connected to the bus. So this can be done through write invalidate or write update mechanisms. So in write invalidate approach, where when a processor writes to a data block, it broadcasts a message to invalidate that block in all other caches. In contrast, write update not only informs others of the change but also sends the updated data, reducing the need for those processors to fetch the new data later. Unlike snooping, directory-based protocols use a central directory to keep track of who owns each cache block and what state it's in. So this directory can be located at a memory controller or distributed across several nodes depending on the system's architecture. Think of this as a library system where a central catalog keeps track of who has borrowed which books and which are due for return, streamlining the whole management of shared resources. So directory-based protocols manage coherence by sending messages only to those nodes that have a cached copy of the data block. This targeted approach significantly reduces the amount of unnecessary data traffic on the bus. So this method is more efficient, especially in large, more complex systems where broadcasting every change would lead to several congestion and inefficiency. So coming to the performance metric comparison, latency, starting with latency, it measures the time from when a cache miss occurs to when it is resolved. So it's critical. It's a critical performance metric because it affects how quickly data can be accessed and processed by the system. So in case of snooping protocols, latency can become an issue in large systems due to bus contention. As more processors attempt to communicate over the same bus, the time to resolve a cache miss increases, leading to delays. Although directory-based protocols experience initial latency due to the time required to look up information in the directory, they generally offer more consistent performance as the system scales. So coming to throughput, it indicates the number of operations a system can process per unit of time. So it's directly influenced by how effectively a system handles data requests and resolves cache misses. So snooping protocols tend to offer higher throughput in smaller systems where bus contention is minimal. However, as the system grows and bus contention increases, throughput significantly decreases. And directory-based protocols scale better with system size, maintaining higher throughput under load. So this scalability is attributed to their ability to manage communication more efficiently by avoiding unnecessary broadcast traffic. So coming to bandwidth consumption, it measures the amount of data transferred across the system to maintain coherence. So in case of snooping, due to its broadcast nature, it typically consumes more bandwidth. Every time a block is updated or invalidated, it broadcasts this information across the entire system, leading to high data traffic. And directory-based protocols, however, are more bandwidth efficient by sending coherence messages only to the nodes that have cached copies of the data block. They significantly reduce unnecessary data traffic. So finally, in terms of scalability, directory-based protocols outperform snooping protocol as they reduce coherence-related traffics with the increasing number of processors, which is crucial in large-scale systems. So while snooping protocols are simpler and easier to implement in smaller systems, they become impractical in larger systems due to the increased complexity and overheads. Finally, coming to a case study done in the book for cache coherence. So this case study focused on a high-performance multi-core system designed to handle complex workloads efficiently. So this system architecture was characterized by multiple processing cores that need to frequently access and update shared data. So this particular system was chosen for the case study due to its high data transaction rates and the critical requirement for consistent data across all processor cores. So they chose Messy protocol for this case study. So the Messy protocol was selected for its efficiency in managing cache coherence. So Messy stands for modified, exclusive, shared, and invalid, each representing a state in the cache coherence protocol that helps minimize unnecessary data traffic between caches. To implement this Messy protocol, they configured cache controllers to manage state transitions efficiently. So this involved optimizing the state of cache lines to ensure that they transition smoothly between modified, exclusive, shared, and invalid states, depending on the cache operation being performed. So upon implementing the Messy protocol, they observed significant improvements in the performance metrics, including reduced cache miss rate and increased throughput. So these metrics are essential indicators of the system's efficiency and response. So detailed analysis showed substantial improvement in processor efficiency and a notable reduction in latency. So coming to this illustration of snooping protocols and validation process in action. So this slide presents a practical illustration of how a snooping protocol manages data consistency through the invalidation process in a system with two processors, A and B, and a shared memory location X. So initially, when processor A reads memory location X, there is a cache miss, indicating that X is not in processor A's cache. So the value of X in memory is 0, so processor A's cache loads this value. Similarly, processor B then reads X and also experiences a cache miss because X is not yet in its cache. So like processor A, processor B loads the value 0 from memory into its cache. Now processor A writes a value of 1 to its location X. Concurrently, an invalidation command is sent across the bus. So this command tells other processors, processor B in this case, that they must invalidate their cached version of X. So this is crucial to prevent processor B from using an outdated value. So after the invalidation, when processor B reads X again, it encounters another cache miss because its cache version of X was invalidated earlier. So it must fetch the new value, which is now 1 from memory. So processor B's cache is updated to reflect this new value, ensuring data consistency across the processor. So while effective for maintaining coherence, this protocol can lead to increased latency due to repeated cache misses, especially in systems with frequent write operations. Each write to a shared memory location can potentially lead to multiple cache misses across the system, as seen in the action of processor B. So now we come to the state transition diagram showing how Messy protocol manages cache coherence. So the Messy protocol, standing for modified, exclusive, shared, and invalid, is a cache coherence protocol used to manage data consistency in multi-core processors. So this protocol ensures that each cache line is different in different caches can be in one of these 4 states, each indicating a specific level of read or write permission and synchronization requirements. So cache line starts in the invalid state when it does not contain any valid data. From here, if a CPU needs to read the data, it places a read miss on the bus, transitioning the state to shared. To shared if another cache is also shared this data, or exclusive if no other cache holds this data. So if a CPU writes to an invalid cache line, a write miss is placed on the bus, typically moving the state to modified directly after the necessary invalidation of other copies. So in the shared state, the cache line can be read by any processor but cannot be written to without further action. If a CPU attempts to write to a shared cache line, it must first signal this intention on the bus, transitioning the state to modified after ensuring no other processes can write to this data simultaneously. So the exclusive state means that cache line is only in one cache and can be both read and written by that CPU. So no bus action are required for writing to an exclusive cache line, but reading from other CPUs will transition the state to shared, ensuring proper synchronization. And the modified state indicates that cache line has altered from its original state in memory and is not synchronized with other caches or the main memory. So it has exclusive write and read rights. When another CPU reads or writes to this block, the content must be written back to memory or invalidated appropriately, ensuring data consistency. So finally, coming to technological advancements on cache coherence. So AI and IoT's rapid data processing demands necessitate advanced cache coherence strategies to ensure quick and consistent data access across processors. The dynamic data requirement of AI and IoT applications challenge existing protocols, requiring faster and more reliable data synchronization. So integration of non-volatile memory technologies such as 3D XPoint alters traditional cache management, merging the boundaries between storage and active memory. So adjustment and coherence protocols are essential to efficiently manage the blend of volatile and non-volatile memories, ensuring quick data access is fully leveraged. Trends towards more cores and mixed core design compel the adoption of more complex coherence protocols to manage increased interaction and maintain data consistency. Diverse core performance and energy profiles necessitate tailored coherence strategies to optimize overall system efficiency. Traditional protocols struggle with scalability in high core and complex memory systems, increasing communication overhead and challenging data integrity. Adaptive coherence protocols and AI-assisted cache management are to be explored as solution to dynamically adjust to changing system loads and data patterns. So in shared now in shared and cloud environments, securing cache coherence mechanism is crucial to protect data integrity and privacy. So future regulations may influence cache coherence protocol designs, necessitating protocols that not only perform efficiently.
So here is the in-class exercise. Thank you, everyone.